So there's our car trying to go up the hill with the angle theta that we don't know what that angle is yet. So if I draw the free body diagram to try and figure out what's going on here, I have mass times gravity pointing straight down. I have the normal force perpendicular to the slope. And then I have the car's attempt to go forward, which I'm going to call capital F. What this really is that the wheels are pushing, the engine's pushing backwards, making the wheels push backwards on the ground, and the ground is pushing forwards on the car because of the effort of the engine in this direction. So this is the engine's effort. The effect of the engine's effort is a push up the hill. But this problem also says that we have frictional forces pushing backwards. Now there was a problem that you might have seen earlier where it's the friction that's pushing the car up the hill. That's different because that's really this force. The friction they're talking about here is the rolling friction on the wheels and the air resistance on the car. So this is the friction working against what you're trying to do, and this one is actually related to the friction that you like. So anyway, this is the car's effort moving forward. This is the frictional forces, air resistance, that kind of thing moving backwards. So we bring in our coordinate system and do our components in the usual way. So in the x direction, we have the car's effort minus friction minus mg cosine 90 minus theta is equal to 0 because it's going at constant speed. We also have the y equation, normal force minus mg sine 90 minus theta equals 0. This equation would be useful for us if we had to calculate the friction, but we don't. They're telling us what the friction is. So if we just look at this equation here, we can find that the force from the car's effort has to be equal to the friction plus mg cosine 90 minus theta. Now, it says, talks about the power. Well, the relationship between power and force is power is equal to force times velocity. And we know the velocity, they gave it to us in the problem. So I can plug in my force into the power equation and get power equals the friction plus mg cosine 90 minus theta times velocity. And then I can solve that for theta. If I divide both sides by v, I get p over v is equal to f plus mg cosine 90 minus theta. Rearrange a little bit more, I find out that mg cosine 90 minus theta is equal to p over v minus f. I don't care that that's ugly because I know all those numbers. So that tells me cosine 90 minus theta is equal to p over v over v minus f divided by mg. From here I plug in the numbers, and so I get cosine 90 minus theta is equal to a number. I'm going to do inverse cosine on the calculator to find out what 90 minus theta is, and then I solve for theta.